Okay, so welcome to the N3AS seminar. Today we have Axel. Axel is a PhD student here at University of Minnesota. He will be talking about distribution function of dark matter halos. Axel, you can take over.
Thank you very much. And I'd like to thank N3AS for the opportunity to give this talk. I'm Axel Gross, as it was said, from the University of Minnesota. And today I'll be talking about some of my research that I've done in collaboration with Yang Chen and Xiaozhou Li on the topic of distribution functions of dark matter halos. So the picture that you see on the title slide is from N-body simulations of dark matter. It's really zoomed out. The width of the picture is 600 megaparsecs, which is much bigger than even the Milky Way. So generally, one of the goals of doing these simulations is to understand the structure that we see. We hope that by understanding this structure, of course, that we can provide some kind of prediction for, the observable universe and help that to match, the cosmological model that we're using, to the observable universe. So, we've had N-body simulations for a while now. What have we learned so far? Perhaps most significantly, we've learned that, the density profiles of dark matter halos can be universally fit. This was shown in 1997 by Navarro, Frank, and White. And they showed that regardless of the initial conditions, regardless, of the cosmology that you're working in, regardless of what time you're looking at, the size of the halo, a wide variety of things, pretty much universally, you get the same functional form for dark matter halos. So what does this functional form look like? It's a simple 2-parameter fit. The 2 parameters are shown. I don't know if you can see my cursor, actually. Let me, how do I add? Yes, laser pointer. You guys can see the red dot now, yeah? I think so. Okay, so anyway, there's the 2 parameters of the functional form are rho naught, which sort of scales the overall density, and r sub s, which is a scale radius, provides a characteristic length scale for the profile. And it's, the profile is 1 over r at small radius and 1 over r cubed at large radius, basically. This profile is divergent. If you take it out to infinity, you get infinite total mass. So obviously in the real world anyway, your halos don't extend to infinity. So it's common to cut this off and define what is known as the virial radius. And you define this such that inside this virial radius, the average density of your halo is 200 times the critical density of your universe. And further, once you define this, it's common to define the concentration of the halo as the ratio between the virial radius and the scale radius in the NFW functional form. And then because you've defined the edge of this halo, based on your virial radius and your average density inside it, you can get the total mass from that. And so basically what I'm saying is you have 2 new parameters with which to parameterize your NFW functional form, your mass and your concentration. And those 2 parameters can basically be used interchangeably with, rho naught and r sub s, the scale radius. So for the rest of this talk, I'll talk about halos in terms of mass and concentration, which you can relate back to the actual parameters in the NFW functional form. So the NFW function profile is, very accurate, useful, widely used for many things. And it's been shown to best fit between 5 and 100% of the virial radius, although it does decently well, above and below that as well, but not as well. The best fit is, in that region. And I should point out that simulations have shown that there is a correlation between the mass and the concentration of the halo. This is a plot from Macchio, 2007. The color spread basically shows, different halos, and you can see that there is a loose relationship between the average concentration of a halo at a given mass, basically. However, this is, there's a pretty wide spread on this. It's far from, a one-to-one correspondence. In effect, these are still independent parameters. What this just means is, you have some typical concentrations that are reasonable for different size halos that you have. So this is the NFW profile. It works very well, but it gives us a density. But if we're interested in learning, more about these halos and their structure, we have to try to understand other things better. So one thing that might be of particular interest, for example, is the energy distribution of particles in your halo. So our goal sort of in this paper is to use the NFW profile to better understand other quantities, which characterize dark matter halos. So how do we do this? Well, really the fundamental object that we're after is the distribution function, which is a probability density distribution in the 6 dimensions of phase space, three of position and 3 of velocity. So, it gives the probability that if you consider a box of phase space, in position and velocity, it's the probability that any particle is in that box, basically. So this distribution function tells us everything about the halo. It tells us the exact positions of all the particles and how they evolve in time. Obviously, it's not feasible to get this distribution function directly. You have a 6-dimensional function that's prohibitive to simulate numerically. You need extremely large number of particles to get basically an equilibrium distribution. So how do we access this distribution function? Well, the first thing we say is that we're interested in equilibrium, halos, and therefore we're interested in steady state distribution functions. So you have, if your distribution function evolves in time, you have to have your particles, evolve with their current position and velocity into the future state. So that fundamental condition, gives you the collisionless Boltzmann equation, which is not, to say that the distribution function is time independent, just that, it satisfies basic continuity. And if you're asking for a steady state distribution function, you're obviously saying, well, the first term in this equation is 0. And so then the second term also has to be 0 sort of independently. So how do you understand what the steady state solutions, of this equation look like? You can define a quantity known as an integral of motion, which you will say is just some quantity that's a function of your phase space variables that does not change in time. It's a conserved quantity. And if you just expand this derivative using the chain rule, you get this on the left. And then if you identify that with, common known quantities like the velocity, you get this expression, which, is the condition for your integral of motion I to actually be conserved in time. And if you look at this, you can identify this as exactly the same as the second term of this expression, which basically says that an integral of motion is a solution to the collisionless Boltzmann equation, and therefore your distribution function is an integral of motion if it's a steady state distribution function. So this was a fact that was first pointed out by Jeans in 1915, which is that any steady state solution, of your distribution function must depend on these phase space coordinates only through your integrals of motion and functions of your integrals of motion. So you can show that, if you build any arbitrary function of your integrals of motion, it's a solution. It's simple to do. It's just 2 steps of math right here. So anyway, what I'm trying to say is that since we're interested in steady state distribution functions, our distribution function must be a function of these integrals of motion. And in the spherical symmetry that we're working in, the integrals of motion are the familiar energy and angular momentum, conserved quantities. So now we've said that our distribution function must actually be a function of energy and angular momentum. And furthermore, we're going to assume that we're working with a distribution function that's actually only dependent on the energy, and that's a property that's called ergodics. So now we've taken this 6-dimensional complicated distribution function and we've reduced it down into a function of only energy. So now how do we relate this distribution function to the density and other quantities that are more physically accessible? Well, it's very simple to relate the distribution function to density. You just integrate out the velocity coordinates. So if you do that and then you make a change of variables, you get an expression here, which relates the distribution function as a function of energy to the density. We can also relate the distribution function to the number of particles per unit energy, N of E, by the density of states. You just count the number. The distribution function is the probability that a state of energy E is occupied by a particle. And so if you count the total number of states, you get the number of particles of energy E. So it's very simple. Once again, you just, integrate over your box, with the condition that you're looking for states of energy E, and you use the delta function to do the velocity integral, and you get an expression for your density of states. And this lets us calculate, the number of particles at a given energy. And this is more physically useful because, you can run a simulation and you can define your box, and you can look at the box and you can count every one of your individual particles by the energy that you have. So this, by combining these two equations, you can relate the density to the number of particles per unit energy. And thus you have a quantity which you can actually measure via simulations, which you also hope to calculate from the NFW density and compare. So this is not as straightforward to solve as it perhaps looks. I will remind you that in this integral, you have the potential, and the potential determines the density. The density obviously determines the potential. So this is really an integral differential equation that has to be self-consistently satisfied. So how do you actually, take your NFW density and access, the energy distribution N of E? You could do that via an Eddington inversion, which, first proposed by Eddington, big surprise, which if you if you take this, top expression on the right, you notice a clever solution to F of E, which satisfies it. And you could write down, a form for your distribution function. And then you can calculate your density of states from the numeric, or from the potential, and you can, multiply to get the number of particles per unit energy. I will say also that it's important to choose the correct region to count in when you do this kind of comparison, comparing between the number of particles per unit energy that is predicted by the self-consistent NFW energy distribution and the actual simulations themselves, because the simulations are not going to be accurate out to infinity. They're not going to model well out to infinity. So the best way to do this is to choose, a box, basically, or rather a sphere. In this case, we'll choose the virial radius, and we're going to count all of the particles inside that. And similarly, to make this comparison line up correctly, when we calculate the density of states for the NFW distribution, we will similarly only count states inside this box. So this density of states integral will have an upper bound on the virial radius, in the integral over position. So basically you're calculating, the number of particles per unit energy that are predicted somewhere inside the virial radius, and you're comparing that to the actual counts of the particles inside the virial radius. And we would hope that we would see good agreement between, the energy corresponding to the potential at 5% of the virial radius and, the energy corresponding to the potential at the virial radius, because that's sort of the region that the NFW profile fits well to begin with. So this is basically what we're going to try to do, is we're going to calculate from the NFW profile, we're going to invert it and find the self-consistent energy distribution that corresponds to the NFW profile. Then we're going to compare it to actual simulations and see how they match. So there's two important things to consider when you do this. The first is that the NFW profile fits very well. However, it can cause large deviations in the central potential region. So here I show two plots of simulated halos versus the NFW profile. This is the potential of the NFW profile on the green line, and then the black data points are of the real halo. And this is the NFW profile that's best fit to this halo. So you can see that even with the best fit NFW, you can have large deviations in the central region in terms of the potential. So what this tells us is that we have to be careful about how we do this energy comparison, because, say energy of, minus 0.6 or so, in the simulated halos versus the NFW is not necessarily corresponding. However, we see that if we sort of line these two halos up, at the virial radius, that is, we define for both cases, we define the energy to be 0 at the virial radius. We see that this gives good agreement, between the simulated halos and the NFW best fit for most of the radius space. So these are two different examples of what you see characteristic in the halos. On the left, you see a small central potential shift, and things agree very well in all regions. And on the right, you see a large central potential shift, and things agree quite well down to 10 or 5% of the virial radius, and then there's a large deviation. And this is to some extent expected because we know that the NFW profile does not fit well inside 5% of the virial radius. And I'll similarly point out that when you do this shift, things agree well above the virial radius too. So we expect that there will be a good comparison, basically above 5% of the virial radius. The second thing that is important to consider is that the best fit NFW profile and the actual simulation, they give different total masses inside the virial radius because you just do the best fit and then it gives a different total mass when you do the integral. The difference is on order 1 to 2%, but when you're comparing N of E, the number of particles per unit energy, if you have more total mass, you should have more total particles. So you need to adjust N of E so that they're, the integral of N of E over the entire region gives slightly more or less, basically. So now a little bit on the sample of halos that we're using. We're using from an N-body simulation. We're selecting halos that are relaxed, and then we're fitting these halos to the NFW profile between 5 and 100% of the virial radius. And then we're, counting the particles inside the virial radius to generate the number of particles per unit energy inside the virial radius. And then we're taking the best fit NFW and we're inverting it self-consistently to find the number of particles per unit energy to compare, basically. So I should explain these plots. On the left, you have the halos that we've selected to be relaxed. On the x-axis, you have the concentration of the halos. On the y-axis, you have the mass. So you can see generally the concentration mass trend. The color of the data points is the root mean squared deviation of the NFW fit, just to give you an idea of how well the NFW profiles are fitting these halos. This is the fit. The root mean squared deviation is in log space. So, 0.1 to 0.15 corresponds to a deviation of 30 to 40%, And then on the right, we have the difference in the central potential between the NFW best fit and the actual halo. So you can see that, generally there's quite a large amount of halos which don't have a significant deviation, but then especially as you get to lower concentrations, there are quite a few halos with a significant deviation. And so that's why it's important to do the comparison correctly. So now if we look at some individual halos and see what this comparison looks like, these are the same two halos that I showed in the potential above here. So one halo on the left with a small deviation in the central potential and one deviation with a large central potential. Once again, the black data points are the number of particles per unit of energy counted from the actual simulated halo, and the green curve is the self-consistent NFW energy distribution that is calculated. The black and green vertical lines represent the central potentials of the two data sets. So you can see that once again on the left, there's a small deviation in the central potential, and on the right, there's a very large deviation. The blue line represents the potential at 5% of the virial radius. So this gives you an idea of the region that we would hope would be accurate. So you can see if you look at these plots, things agree relatively well, especially above 5% of the virial radius. For halos that have a small shift in the central potential, things agree well even below 5% of the virial radius, or rather the potential at 5% of the virial radius. But you can see if there's a large shift, the NFW profile is essentially, forced to zero because it's reaching the central potential, but that's very close to 5% of the virial radius for the actual halo. So you can see that there's large deviations. But if you, go up a little bit more to say 10% of the virial radius, which is around where minus 0.4 is on these axes, you have good agreement, all the way up to the virial radius. And then there's also good agreement above the virial radius in the tail. So what that says is that the NFW profile, while it may not necessarily be accurate all the way out to infinity, the number of particles that you would predict inside the virial radius of higher energy particles is about the right number if you just assume that the NFW, continues to infinity, basically. So then if you kind of do this comparison for all of the halos in your simulation, this is what you get. So on the left, we have the individual data points or individual halos as a function of concentration. On the y-axis is the difference in the central potentials, and then the color of the data points is the root mean squared deviation of the, between the green curve and the black data points, again, between 5 and 100% of the virial radius, or rather the potentials at 5 and 100% of the virial radius. So you can see that, once again, if the shift is small, things agree quite well. Then if the shift is large, you start to see larger deviations. This is because of this region right here, where you have, the NFW profile for large shifts is essentially forced to zero. And this root mean squared deviation is calculated in log space. So you have many orders of magnitude difference, and that's why the deviations are so large. And you can see that if you compare that to the plot on the right, where I instead calculated the deviation between 10 and 100% of the virial radius. And you can see that the deviations are much lower. And in fact, these values are, between 0.05 and 0.15, which is about the same order of root mean squared deviation that you see in the fit to the NFW density. So what I'm basically saying is you have a certain amount of error when you fit the NFW profile to the actual density distribution. And then if you invert that and you compare the energy distributions, you basically see the same amount of error. So that's pretty reasonable, and that's a good thing. So then you can move on and you can try to compare the distribution functions themselves directly. So if the halo is fully equilibrated, you should have a uniform distribution function. It should apply to the whole halo. We can calculate the distribution function from this halo by using the numerical potential. As I said, it's difficult to directly calculate the distribution function, but we can take, the counts of the particles N of E, and then we can take the numerical potential to calculate the density of states, and we can define what to infer what F of E, the distribution function, should be. So if we do this for two different sample regions, counting inside the virial radius and counting inside 2.5 times the virial radius, this allows us to test the equilibration of the halo, because we expect that it should be, if the halo is perfectly equilibrated, you'll get the exact same thing, even though you count a higher number of particles inside 2.5 times the virial radius. Your density of states is higher, and it should cancel out if it's perfectly equilibrated. But realistically, it's not going to be exactly the same. Additionally, we can compare these distribution functions that we calculated to the distribution function of the best fit NFW profile. And once again, we have to be careful about how we do this comparison. The distribution function is the probability per particle in your sample that a certain state is occupied. So if you have more particles in your sample, your distribution function will be naturally lower. So if you want to compare, two different samples, where there's a different number of particles, the proper metric to compare is actually, the distribution function multiplied by the total mass of the system, basically. So if you do that for the two halos that I've been showing, this is what you get. The blue curve is the calculated distribution function from the halo inside one virial radius. The red curve is the distribution function calculated from the halo when you count with inside 2.5 times the virial radius. And the green curve is the distribution function of the best fit NFW distribution. And the black line is the potential at 5% of the virial radius. And once again, you see a similar story. If the shift on the left, you have a small shift in the central potentials, and the distribution function agrees very well, basically from the central potential energy all the way out above the virial radius, to the fall off energies. But if the shift in the central potential is large, you start to see deviations around 5 to 10% of the virial radius because of this shift, basically. Additionally, if you look at the comparison between the blue and the red lines, they're very similar. And so therefore you expect that, basically this says that, in fact, we have picked out halos which are equilibrated, basically. So in conclusion, the NFW profile provides a good approximation to the density profiles of dark matter halos. And we've shown that with proper consideration, we can generate an energy distribution from this NFW profile, which agrees well above energies corresponding to 5% of the virial radius with the simulated halos. And we also find good agreement with the distribution function of the NFW profile with that of simulated halos. And we also find that the halos are reasonably well equilibrated. Furthermore, we find that the NFW profile gives us a good model for the tail of the energy distribution that you observe inside the virial radius, even though the NFW profile is not necessarily in agreement all the way out, to infinity, obviously. So those are my conclusions. Thank you. I will take any questions that you have. I see George has raised his hand.
Thanks, Axel. That was great talk.
Yeah.
You gave a great talk in Seattle too.
Yeah, it was slightly different, admittedly, in Seattle.
This is slightly different, and it helped me. So my question is this: really, if all of this is done with the collisionless Boltzmann equation, so it's really. Yeah, so my question is really when it breaks down, right? Because it's clearly going to break down at some point from two-body collisions.
Yes.
Even gravitational collisions.
Right.
So, and that's going to break down if I make the lumps of dark matter larger, or the lumps of density larger, right?
Yes,
so
yes.
Capital N gets smaller.
Mm-hmm.
And I'm just wondering if presumably that's only in the very center of these. Is that right?
Well, first of all, you have to keep in mind that we're specifically selecting equilibrated halos. So our conditions for selecting these halos, for example, are that there's no subhalos inside 2.5 times the virial radius. There's no overlap within 2.5 times the virial radius within another halo.
Which is where you'd expect two-body encounters.
Right, exactly.
Okay,
so yes, I mean, our assumptions for this entire thing are that you're working with a relaxed equilibrated halo, and we tried to select conditions to model where that is the case. And, if that's not the case, well, yeah, obviously things become way more complicated and perhaps interesting.
I mean, it is interesting though, if you put dark matter in compact dark objects, for example, make lumps out of lots of light particles and make big lumps out of them. And at some point, there will be some two-body encounters that are important.
Sure, of course, definitely. At the moment, they're completely ignored.
Very good. Thank you, Axel.
Hi, the next question is from Kyle. Kyle, can you please unmute yourself?
Hi, Axel. Great talk. Thanks for that. I think there was a similar talk you gave over in Santa Cruz.
Yes,
or at least there's some plots that are the same. But yeah.
Yes, yeah, it's similar.
But still, good talk also. So I have a couple questions. So how did you determine in your simulations which halos were relaxed, like sufficiently relaxed for the virial theorem?
So basically, the conditions that we used were that there's no subhalos within 2.5 times the virial radius. Then there's some condition on what qualifies as a subhalo. I think it's no subhalos bigger than 1/10 of the mass of the actual halo. And then there's no overlap between these halos and other halos. And then the third important condition is that the potential, if you calculate the numerical potential of the halo itself, that this potential is sufficiently close to the center of the halos, because you see for some halos, basically, the minimum of the potential is not actually close to the center of the halo, and thus definitely it's not completely relaxed yet. So those are basically the conditions that we used.
Okay, cool. And then for this, my second question, when you did, what was it called, the Eddington inversion?
Yes.
I haven't seen this before, or maybe you showed this in your Santa Cruz talk, but at least I haven't studied it myself. I looked this up briefly to get a somewhat decent grasp on it.
Mhm.
Let me see. So according to this source, at least on the archive, it says that the potential needs to be monotonically decreasing in order to do this as a function of R.
Yes.
Would that be usually true for galaxies?
Yeah, should be.
It should be? Okay.
Yeah.
Okay, I'll believe you. Okay.
Yeah, I mean, you have,
But
I mean, the potential has to, I mean, if they're saying the potential is monotonically decreasing, they're
Yeah.
probably talking about the relative potential, which is, upside down, basically.
okay.
Because like if you imagine a potential well, right? Just I'll talk about the normal potential, there's obviously the, energy equals 0 at infinity. And then as you get closer, it gets, you get more and more bound until you reach the center. And yes, so at least
right.
At least if they, so that's kind of upside down is what they're saying, because normally in these kinds of things, they often work with the relative potential, which is defined to be minus the potential, basically.
Okay.
So that's probably why
yeah.
it says monotonically decreasing. But the point is basically, yes, if your halo is equilibrated, your potential should get stronger and stronger as you get towards the center of the halo, basically. So
Okay,
I guess if your
yeah, that
halo
makes
is not
sense.
relaxed, you probably don't have that condition
Right.
necessarily. But certainly for the NFW profile, which we're actually inverting, that condition is satisfied.
Oh, okay, I see. Okay. Yeah, I was getting it confused with including the centrifugal force for the
Yes.
effective potential, but okay, never mind. That makes a lot more sense.
Yeah.
Okay, thank you.
Mhm.
Yeah. Thanks, Kyle. The next, Serud, can you unmute yourself and please ask your questions?
Yeah, thanks again for the great talk. I was also curious about the distributions of halos that you're looking at and how much angular momentum they can have.
I must admit that I do not know the answer to that question.
Okay.
I did not do the simulations myself. I more or less, I can ask my collaborators and get back to you if you'd like about that.
I'm just wondering if there's enough for a significant deformation, which would cause deviations from any kind of spherically symmetric analysis, right?
I would think not, given that we're specifically trying to select sort of the most ideal halos for this situation, basically. But I cannot say for sure.
Okay. Thanks.
This paper will hopefully appear on archive within a few weeks, so you can keep an eye on that too. Maybe there will be more details in that.
Sounds good. Thanks.
Okay, thanks, Serud. Susan, can you please unmute yourself?
Oh, thank you. That's a nice talk. Thank you very much. I guess I wanted to ask some of the questions that have already been asked in a slightly different way. That is to say, purposely picked subhalos that have no overlap with other halo galaxies or isolated. And I think that it might be interesting to try to stress test what you have done. So for example, you made sure that it was as isolated as you can make it, and no overlap with another with another subhalo in the Milky Way, for example. And I wonder how quickly does these comparisons degrade if you allow things to be closer together, or if there's any overlap? I'm just wondering.
Yeah, I don't think we've tested any halos where there is some kind of overlap. It would obviously depend, I think, I'm not saying anything novel here, but I think it would obviously depend on the degree of overlap and the severity of it. And at some point, as you said, it will degrade. I can say that if you look at halos where the third condition is satisfied, that is, or the third condition is not satisfied, that is, the potential does not have a minimum at the exact center of the halo, you really start to see quite bad fits to NFW to begin with. And then when you do this inversion, you see the same thing, basically. So at the very least, I would say that condition has to be relatively strongly satisfied. That is, the condition specifically is that the minimum of the potential, we picked halos where the minimum of the potential is inside 0.01 virial radius. so 1% of the virial radius. And if you look at the halos where the minimum of the potential is, somewhere outside 1% of the virial radius, things are quickly degrading already.
Okay, and the only comment I would have is that if you have, in fact, an ergodic distribution function, then it would be manifestly spherically symmetric. And
Mhm.
therefore, this issue of what L is strikes me as moot. And so
Yeah.
I guess I would say that. And then the other question is that, particularly in discussions of, looking at the structure of subhalos bound within the Milky Way, there's a lot of discussion of what the distribution function or effectively mass density does at small distance. But it seems that you cut away that altogether. I mean, from this particular discussion, not wanting to go within 10% of the virial radius. And I
Right.
wonder if it's something that you could systematically look at what kind of distributions. I guess your numerical simulations all presuppose cold dark matter.
Right. And there's no baryons or anything in them either. So obviously,
No baryons either.
yeah.
Okay.
So obviously, once you look at small radiuses and include baryons, things can be very different.
Right.
So I wouldn't, try to speak generally. I mean, obviously, I agree that's something you could try to do. But I can't say that I have any.
I just was curious because
Yeah.
it seems to be a hot topic. I
Yeah,
mean,
yeah,
what exactly is happening in a core subhalo? But
No,
I
I
think it's
agree.
nice to have this existence proof
Mhm.
that if in fact you explicitly solve for the ergodic distribution function, that you confront, there are regions of which you confront NFWs successfully. I think that's new. I don't think that I don't think that's been done previously.
I hope so. I mean, that's kind of the goal in publishing a paper, right? Something new.
No, I was trying to find, I wrote a review article and I thought there was some, I was trying to find the reference with similar work. If I can find it, I will send it to you, of course. Okay.
Yes, thank you. No, I mean, I'd say the real conclusions of what we've done are basically that if you have a well-fitting NFW, it does, through this inversion, provide a good model for the energy, provided that you basically look in the correct energy region. So you can, I mean, the NFW profile has been extremely useful for, modeling densities of halos, but it's possible it has other uses too, in terms of finding the energy distributions and distribution functions.
Okay.
So
We'll see.
yeah, we'll see. I don't know.
Yeah, thanks, Susan. So are there any more questions for Axel? Are there any more hands in the chat? If not, then let's thank Axel one more time. Thank you for your very nice talk, and thank you everyone for making it successful one. Okay, we will meet next week.
Thank you.
Thanks, Axel.
Thank you.
Thank you.
Thank you. Bye.